All right, so let's get going. So this is actually, we've got a lot to talk about today. I am going to go over the second and last project today in great detail. So get your questions out of the way today. There's lots of things. And I made one. It's not as much of a mistake as it's kind of a mistake. It will not affect the actual output at all of your program, but I'm going to try to change it such that people don't get too confused. I'll tell you where that happens later. Pac-Man is done. We are grading it now. All done. We're on to the final project. And the final project, as I said, I will go through lots of detail in the final project today. And it involves, some of the final project involves strings, right? Because you are taking text and you are encrypting it and you are decrypting it and you are telling whether or not a sentence has words in this dictionary, right? So you're basically going to take a bunch of text and say how many of the words in that text are in the dictionary. You have to figure out how to break up a string into words, right? Well, what is going to break up two words in a string? Space, right? So we're going to have just spaces and characters. So you're going to go through the string and you're going to figure out where the spaces are so you know where the words are so you can do this. You will practice some of this in lab this week, okay? So you'll get a little bit of practice with strings. But anyway, that's what we're going to talk about today. Are there any logistics questions before we get going? Yeah, Jacob. Oh, you'll see what's up with the font. You'll see. We are going to talk about history of computing. We are going to talk about the project for most of the rest of the class. At the end, if we have time, we'll talk a little bit about reading from a file, which we've done for you for the project. So you don't need to know how to do that. But the nice thing about this project is, if you ever go back and want to do some other programming on your own, this is a good project to go back and look at how things are done. If you want to read from the command line, in other words, you know when you type clang ++ and something and something and something and something, that's the command line. Your programs can do that. If you type your program name and then something and then something and something, you can read that into your program and tell what the user typed. Kind of cool. That's one thing that you'll be able to do in this project. You do not need to know how to do that. We've done it for you to show you how it's done. You also can read from files, which we've also shown you how to do. So if you go back and want to do other projects later, this is a good one to go back and look at to go, oh, how do I do that? Oh, we did that in that project. So good idea. All right, so we're going to do that. Let's first talk about history. This guy, this is Edgar Dykstra. He passed away a few years ago. He is was from the Netherlands. He is another huge giant in the field of computer science. Okay, we've talked about a few already. We've talked about Dennis Ritchie. We talked about Donald Knuth. We talked about Grace Hopper. We've talked about some of the big names in computer science. This is another one. All right. Ada Lovelace, that sort of thing. So he was one of the first scientists to call himself a programmer. So it turns out in the 1950s, computers were so new that the term programmer didn't really exist. It was kind of coming into being. And there really wasn't a computer scientist yet, right? If you were doing computers, you were probably either a physicist, or you might have been an electrical engineer, or you might have been a mathematician. All of those types of people were the ones thinking about computers because physicists needed to figure out how to build the things, right? The electrical engineers, same thing, they were building them. The mathematicians were the ones doing how do we compute things and all that, right? Well, Dykstra comes along, and he was actually a theoretical physics major when he was in college and did theoretical physics. And then he started using computers in his job, and he said, whoa, this is really cool. So he started doing that, and he started calling himself a programmer. In fact, he put it on his marriage certificate when he got married, like a job. And I guess in the Netherlands, anyone from the Netherlands here? I don't think there are. I guess this might not be true anymore, but in the 50s, if you're from the Netherlands, you had to put your job on your marriage certificate. And they looked at that and went, oh no, you can't get married. That job doesn't exist. So he had to put something else. I don't know what he put. And then maybe he put mathematician or something. But anyway, he was the first one to call himself a programmer. So what's his big deal? He was so influential in so many different parts of computer science. Compilers, clang++. Now he never used clang++, or he didn't do clang++, but you wouldn't have clang++ if it weren't for Edgar Dykstra, because he did a lot of theory on compilers. Operating systems. You wouldn't have your Mac or your PC operating system for him because he did a whole bunch of stuff in operating systems. Concurrent programming. You know how I've talked about this before. Your computer has probably 2 or 4 different cores in it. Each core is its own processor. How do you make those cores work together? How do you do a program that can use both of those cores at the same time? He started thinking about that way back when. Algorithm design. All these different types of algorithms we might be talking about. I'll talk about one in particular in a minute that he's famous for. He did programming languages. I don't think he did too much in C++, but he talked a lot about other programming languages, especially in the early days. And then teaching. He was very big into like saying, hey, we have to get people like you guys to know some computer science so that we can make this field grow. So pretty cool. It would be really hard to say what he did that was most influential because he touched so many different parts of computer science. One notable algorithm that he did is this algorithm called Dijkstra's algorithm. And what it was it's an algorithm to find the shortest path between 2 points in a graph. And by graph, I don't mean like a chart with like economics or whatever stuff on it. I mean this. It has a whole bunch of what we call vertices. They're just nodes, by the way. You could call them nodes. We generally call them vertices. And they're connected to other parts of the graph through these little lines that we call, why am I blanking on it? Edges. That we call edges. So the vertices are connected by edges in this little graph. And what his algorithm was used for is to determine the shortest path between 2 vertices on a graph. Where might you use this? How many people have used Google Maps before? Or Apple Maps or whatever, right? Pretty much everybody's used these things. What that is if you want to drive from here to Florida, right? Your computer, through Google Maps, can tell you the shortest distance to get, shortest path to get there. Now, when I say shortest path, do I necessarily mean number of miles? No, what else could I mean? Time, right? If you're going on the highway, it might go meander around big cities. But if it's got a speed limit of 70 miles an hour, you're going to be able to do that faster than going right through the city at 30 miles an hour with all those stoplights, right? Time's a big one, even though it's shorter distance going through the city, right? So time's a big one. Distance is a big one. What's another one that might be a big deal? If you're especially going through a city. Oh, money could be one. Yeah, I mean, you might, maybe it costs more to go tolls or something. Maybe it counts tolls or something like that. That might count, or amount of gas you're going to use or something. But I was thinking more like traffic, right? Traffic might be a big deal. Google Maps does a pretty good job of this, of figuring out what the traffic is and saying, no, you don't want to go that way. You want to go this way instead. Hasn't figured out construction very well, but they're getting there. So anyway, Dijkstra's algorithm was the algorithm that says, if I know that it costs me 14 whatevers to go from here to here, and it costs me 9 to go here to here, and then 2 to go here to get from here to here is better to go this way than to go this way because it's less than 14, right? And there's an algorithm to do that. It's actually not that hard an algorithm, but Dijkstra was the first one to come up with this. So things like Google Maps use either Dijkstra's algorithm or another very similar algorithm to do that. So pretty famous for that. You will talk about Dijkstra's algorithm at the end of Comp 15, and you will talk about it again in Comp 160, and you'll go into much more detail about it. Okay, so that's Dijkstra there. Another thing about Dijkstra, very influential in making programming languages more structured. Okay, in other words, we've been hammering you guys all semester about making things modular, making sure you have structure in your programs, making sure that they're well written. Dijkstra is one of the ones who said, hey, there's this thing, back then this was in almost all programming languages, was this thing called goto. It actually does exist in C++. You'll almost never use it. What it means is if you're in a function, you can go from any line on your function to any other line on your function immediately. Right? If you're in the middle of a for loop, you can jump to some other part in your function, then jump back and all this. This leads to what we call spaghetti code, which is code that's so hard to understand because it's got jumps all over the place like spaghetti, that it's not a very good way of coding. Using gotos, Dijkstra came up with this, had a paper called Goto Considered Harmful. It's actually a kind of a famous paper now. Goto Considered Harmful. And here's a little XKCD comic about using goto. It says, I could restructure the program's flow or use one little goto instead. And he says, screw good practice. How bad can it be? Then he types go to main sub 3 and then compiles it. And then he gets eaten by a velociraptor. So don't use goto in your programs. All right. Anyway, Dykstra was influential there. Another thing about Dykstra, I'm going to turn the lights off for this. Dykstra may, in fact, be Walter White. Don't they look like identical? I think he might have been Walter White. Probably, I don't know if he ever made meth in his backyard, but I doubt it, but you never know. He also, what I love about Dykstra is that his name has an IJK in it, right? D-I-J-K, it's very rare that you see that, right? This is why we use IJK in our loops. Actually, it's not at all, but it would be kind of cool if that was the case. You can tell all your friends that that's why we use IJK in the loops, because Dykstra has IJK in his name. All right, so that's the thing about Edgar Dykstra. Now, he used to write his papers. Remember, this is like the 1950s. He probably had a typewriter, but he decided to write most of them by hand and literally sent them in for publication in his own handwriting. He had really nice handwriting. So nice that somebody made a font out of it, and this font is his handwriting. So that's actually true. The font we're using today is Edgar Dykstra's handwriting made into a font. So it's pretty nice, huh? I would love to have that kind of nice handwriting. But, yeah. OK, that's Edgar Dykstra, another giant computing field. He actually worked at University of Texas after he left Netherlands in, I don't remember, the 80s or something, and they gave him a job at University of Texas. Anybody from Texas in here? No Texans? There was one in the last class. Anyway, that's Edgar Dykstra. OK, project 2, final project of the year. Encryption. Hopefully you've already read over this and maybe started coding it a little bit. If you haven't yet, that's OK. But remember, phase 0 is due Sunday. I think phase 0 is easier than phase 1, as it turns out. You just have to figure out what's going on with these linked lists and why they're different than some other linked lists. But we're going to go over all that today. Your job, the big idea here is that you have this text we call plain text. And it's the quick brown fox jumps over the lazy dog, right? And you've got that. And then we're using a key or a password to encrypt that into something unreadable by scrambling all the letters. That's how the encryption works for this program. Okay, it just scrambles all the letters, and that's how it works. We aren't going to give you the key for these decryptions. We are going to give you a set of keys, one of which will work. So you're going to have to read in all these keys into your list that you're going to build in a linked list. And then you're going to use all of those, and you're going to apply this decryption to them. Now, we've already given you the decryption as well, so you don't even have to worry about that. If you want to worry about that, go right ahead and look at the cipher the cipher class and see how we did it. Right? It might not be perfect, but it does the job the way we want it to. And so you can use that to do it. If you want to look at it, go right ahead. But your job for this project is twofold. First, you have to make a linked list class called keylist, which has an iterator. We're going to talk about what an iterator is later today. Okay, it's got this iterator, and it's going to hold the keys, and it's going to walk through those keys and do something with them. You are then going to make a dynamic array class called dictionary. And the dictionary is going to hold a whole bunch of words. How many is a whole bunch? 200,000 or 300,000 words. And it's going to hold all those words and be able to search through the dictionary for a particular word. So in other words, if you've got the quick brown fox jumps over the lazy dog, you're going to check the. And you're going to say, is it in the dictionary? The dictionary is going to say true. And you're going to take quick and do the same thing. But if you have something that's scrambled that isn't in the dictionary, it will return false and say, nope, that's not in the dictionary. Okay? On Thursday, we will talk about a fast way to search through your dictionary, much faster than going, is this the word, is this the word, is this the word, is this the word? Okay, we're going to talk about that, which should be kind of fun as well. You do not have to implement the fast method, but it will make it much faster for what it's worth. Okay, anybody confused on the big idea here? Okay. You've got a bunch of definitions. Okay, they're in your handout. You should kind of know these. They're not hard. Encrypt or decrypt is to change a readable message into an unreadable message with a key. To decrypt, encipher or encrypt. To decrypt or decipher is to go back and change it back into readable text. The key is what you're using to do the actual encryption or decryption. Brute force means you don't have the key. You're going to try lots of different choices for the key. Plain text is the actual readable, human readable text. Ciphertext is the unreadable encrypted text. Those are the big definitions. OK, here's how the program will actually work or look to the user. You will type, for phase 0, you'll type /phase0 -- encrypt and then some key. And then you will type in a bunch of text that you want encrypted. And the cipher will spit back out this, where it did two things. It converted all of the spaces to underscores, and it scrambled the entire phrase. OK? So it's almost impossible without knowing the key to go back to this. Yeah?
So does the second one have exactly the same letters as the first one?
Yes. The second one has exactly the same letters as the first one. Notice there's, let's see, how many S's are up here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
So
it may have a different number of spaces for what it's worth, but only off by a couple.
So it would be hypothetically possible to figure out that it is like
Oh.
English just by figuring out like the occurrence of
Yeah, you could probably figure out it was English.
Oh, yeah.
But would you know where all the letters are? No. There's lots of different choices here. Yeah, lots of different choices. Yeah.
Does the T get uncapitalized?
Yeah, so what happens is you can type anything up here. It takes everything out that's not a number, or sorry, not a letter or a space. Everything else gets removed. Yeah, good question. Yeah. Same question? Yeah. So it gets removed. And we all did that. We did that for you. Although you'll look at similar things like this today in this week's lab on how to do that. OK. You have to be able to encrypt this way. You also have to be able to decrypt this way. This is for phase 0 and 1. It's going to be the same. Same thing. You type -- decrypt and then ABC123. And then you type the text. And then you basically paste this in, or copy it directly, but paste that in the ciphertext. And then it will print out the actual plain text. It goes backwards. OK. If for phase 0, what you're going to do is it's going to look like this. You are going to type phase 0 -- key file and then give it a key file. This happens to be in a different directory the way I did it, but you're just going to basically say 10 passwords.txt or 100 passwords or 1,000 passwords or whatever that key file is. And then you're going to type the stuff to decrypt, and then it's going to decrypt it for every one of those keys. And it's going to say, here's the decryption for shadow. Here's the decryption for let me in. That doesn't look like English. Here's the decryption for monkey. Here's the decryption for football. Here's the decryption for ABC123. Oh, look. That looks like that might be the right decryption. Yeah?
So I understand what this means with the key shadow, key let me in.
OK, there's going to be a file that's going to have the following words in it. Shadow, let me in, monkey, football, ABC123, baseball, dragon, da-da-da. Those are the top 10 most used passwords.
Okay.
Right? You're going to read all those in. We've actually written the function to read those in for you. You're going to put them in your linked list. Then you're going to walk through your linked list and check every one against this using the function we gave you. And then it's going to print out, hey, you tried shadow. This is what came out. You tried let me in. This is what came out. You tried ABC123. This is what came out. Oh, that's probably the right one. The password is probably ABC123. Make sense? No?
I just want to see the relation between the password and its encryption of the message.
Yeah, this is trying to decrypt it.
Yeah.
So this is the ciphertext. I give this to somebody, and you're a bad guy, and you steal it, right? And you go, I want to see what that says. Well, this is what you're given. And we have a password. We have a decryption function, which takes anything in and tells you what the decryption is. If you give it shadow, this is what comes out. Is that what I pass? No. If I give it ABC123, this is what comes out. Aha. That's what it is.
If it's the right password, then you can see that.
If it's the right password, it's the right message. Yeah, you can see the right message. Now, for phase 0, one sec. For phase 0, how do you tell which one's the right one? Yeah.
You check it against the dictionary?
No, not for phase 0.
Oh, okay.
For phase 0, you use your eyeballs. And you say no, 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 yes. That's how you do it, right? You use your brain and your eyeballs, right? For phase 0, you do. For phase 1, on the other hand, then we use the dictionary. Question?
Yeah,
Sure. Well, it kind of does. That is the key I used.
Right, but the only reason it works.
Well, the only reason it works is because it's the right one. Yeah, that's the only. There is no other way of figuring it out in that case. Yeah, good question. Anybody else on this one? Okay, for phase 1, on the other hand, then you get to the real cool part. You say, same thing, you say, okay, here's my key file. You enter the text, and then it says, checking, shadow, let me in, monkey, football, ABC, 1, 2, 3, baseball, dragon, 1, 2, 3, 5, QWERTY, password. And then it says the top 5. Actually, I didn't put it here, but it should say something like the top 5. This is my secret message, decrypted with key ABC, 1, 2, 3, 100% match. Awesome. His, tie, psi, smuk, eddergzms, e. Decrypted with shadow, 67% correct. Why is it 67% correct? Well, guess what? His is a word in the dictionary. Turns out so is like tie for whatever reason. It's a big dictionary, right? And I think SMC might be as well. I don't think eddergzms is. But anyway, 67% of those 6 words, 4 of those 6 words are in the dictionary. And you print out the top 5, right? And the odds are very, very good that the top 1 is going to be your answer. Sometimes you might get the top 2, but that's why we're having you print the top 5. See what I mean? That's going to be phase 1. Okay. All right. For phase 0, you're going to use this key list, and we're going to talk more about that now, to read in all the potential keys. So we read in the list of all the potential keys, and then you're going to print out all the decryptions using those keys. Okay? We get to choose what the keys are. We get to pass in, when we test it, we'll pass in some key list, and we'll see how it does. In fact, I'll give you a bunch of tester ones, so I'll encrypt a bunch of things, and you'll be able to use your program to tell what they are. Kind of fun. All right? Phase 1, you're going to use this dictionary to read in the words. Then you're going to use the key list to decrypt every key. Then you're going to use the dictionary to check each decryption for the number of words that are in the dictionary. You're going to store that information, and then you're going to go back later and you're going to say which ones are the top 5. Okay? You're going to store the percentage of the words in English, well, from the dictionary, and then you're going to print out the top 5 highest percentage. Okay? All right, for phase 0, what kinds of things are we going to have to do? We're going to have to build the keylist class. So you have a keylist.h file. Keylist.h file has the 2 constructors in it. One constructor is if you do not have a file name. The other constructor is if you do have a file name. You need to write both of those. You've got the destructor, which in this case you're going to have to write a destructor that that destroys your list when it ends. So we're going to check. We're going to use a program that actually checks to see if your memory was freed correctly. If it wasn't, you'll just lose a point. The insert function. This is going to be very, very similar to your lab last week. So if you don't know how to write your insert function, go look at last week's lab and go, how did we write the insert function there? And then apply it to this problem. The next function. This is a new one. This relates to the iterator, which is traversing your list from outside the list. I'll show you what that means in a few minutes. And then you've got a reset iterator, which basically just says start over from the top. In other words, start from the top of the list. And then the update result function. The update result function you don't need for phase 0, but it will be for phase 1, where it will take the result of your decryption, put it into a variable, and put the percentage of words in there. Anna, don't look so sad.
I was just wondering what the next function is.
Oh, we will talk about what next is. We'll get that in a few minutes. OK. And then you're going to have to modify phase0.cbp. It's like 90% written for you right now. OK? You have to write a couple things. You have to write the decrypt function. So I talked to somebody yesterday who said, oh, I did the decrypt function. It took me 1 minute. Because it is exactly the same as the encrypt function, which I've already given you. So don't stress about writing that. All you have to do is take 1 minute and go, oh, it's exactly the same. Boop, and you're done. That's easy. The harder one is brute force, which is the one where you have to go through your list, check all the encryptions, and then print them out. It's actually fairly straightforward. It's a while loop, and you're just going to go through the entire list and print them out. So the hard part is just getting the key list built by the end of the week. The easier part is just going through all of them and printing them out. So I don't think phase 0 is that hard. Phase 1 is going to be a little harder, I think. OK? Let's talk about some of these things. if you look in the keylist.h class, we have a struct called key with result. Now, I screwed up in this. The result when you've decrypted is plain text or ciphertext? Yeah, when I've decrypted it, what does it become? Plain text. I called it ciphertext here. I screwed that up. So I'm happy if you leave it that way. You can also change this to plain text. I will probably update if you haven't downloaded this yet, I'll probably at the end of, like after today, or after this class, I'll go change all these to be some plain text and then just update everything. So if you haven't done anything yet, just recopy those maybe tonight or tomorrow morning. If you've already started working on it and already started using cipher, just leave it. Do not worry about updating that. In fact, the nice thing is you don't really need this at all for phase 0. So I can fix it before phase 1 and it should be OK. But I'll tell you what to change. It was just dumb that I screwed that up. But anyway, the point is, this is a struct that has 3 things in it. It's got a key. It has a word percentage, which is how many of the words in your decrypted phrase are in the dictionary. And it's got the decrypted phrase in it. OK, it's got 3 things in it. And it just looks like, in memory, it would look like this. I'm going to abbreviate KWR, might be the actual name of the variable. In fact, it is. You'll see in a minute. It's got 3 things. It's got a key. It has a word percentage. I'll abbreviate WP. And it has a ciphertext, which should be plain text. But I'll abbreviate it CT for now. OK? That's the actual data we're trying to store for each word that we're trying to use to decrypt. OK? It's a struct like this. Now, when you talk about your linked list, we have done our linked list so far like this. And then let's see, this one is null. And each one of these things is the data. Now this is going to be a key with result. And this is going to be a key with result. And this is going to, it's not going to be a simple int or a simple string anymore. It's going to be that struct. OK, we're abstracting this a little bit more. OK, let me show you what I mean. Any questions on what these 3 things mean? Yeah, Tony.
I'm confused how the linked list is going to be filled with key with results.
Yes.
But isn't that what we're creating?
Kind of, yes. But so basically, you're going to do this. You are going to read in a bunch of keys. And what you're going to fill in your linked list are a bunch of key with results at the beginning with just the key in them. You're not going to worry about the word percentage. You're not going to worry about that because we haven't done that yet. You're not going to read those in yet. You're going to just insert just the keys, right? So you're going to have A, B, C, 1, 2, 3. You're going to have password. And the other 2 are going to be, and the other 2 parts are going to be dead squirrels at the beginning. Doesn't really matter. Yeah? Question in the back? No. OK. So that's that. Now, let's look at the actual node. This should look somewhat familiar. You have a node that has 2 things in it. One is this key with result. That's the data. The other is the next pointer to the node. So in the nodes, you've still got a next pointer here and here and here. OK? And that's what it's going to be. It's going to be a key with result, key with result, key with result. And the next pointer is going to be the part of the node that points to the next one. As I said, we're just abstracting this out a little bit. You've got data. I could have just called it data instead of KWR. But I call it KWR because it's a key with result. And then you've got next in there. OK? Yeah?
So if I want to access the key within the key result thing.
Yeah, this is so Jacob brings up a very good point. Here's your head. Now, we haven't talked about this yet, but let's say that we had an iterator. An iterator, which is another node pointer. And it points to this node here. OK? It's a node pointer. And it points to this node right here. OK. If it points to that node, how would we refer to the KWR object in the iterator's node? How would we do that? Do you guys remember how to write that out? Yeah, Will. Yeah, it's the arrow. Iterator.
Greater than sign, yeah.
Yep. And then KWR. And that tells us, that doesn't look like a KWR, hold on. KWR. That tells us this object right here. If I want to refer to this object's key, what do I need to tack onto that? Dot key, right? And that will tell us, go to iterator where iterator is pointing, grab its KWR, member, and then go to KWR's key member and get that. Yeah?
And it's easy to move the iterator between each link?
It is. We'll get to that. Yep, we'll get to that. But the idea is this is now your linked list. Okay, this is now your linked list. Okay. All right. Now, here's an example list. Does this list make sense? You've got, this is, by the way, probably it would look like this at the end of phase 1 because these are filled in. But it's going to be the head pointing here. It's going to be ABC123 0.0 and then some not very well decrypted text here. And then it's got a next which points to here. And this one's got something else. This one happens to be perfect 100% and it's some text. You can read it. Next, and then football, whatever. And then this one's no. That's what your linked list is going to look like. Okay. There's the data for the first node. There's the data for the second node. There's the data for the third node. Let's talk about this weird next function. OK. If I have my linked list, let's call it, I don't know, my key list, we'll call it KL is my key list. If I say keylist.next, okay, that means give me the next key with result from the list. That's what it means, okay? So it means it's going to be able to walk us through the list one by one and give us back the information we're looking for. Okay, it's traversing the list, but doing it every time we ask for it. Every time you call next, you get back data from the next node in the list. This is where the iterator pointer comes in. The iterator pointer keeps track of the current location. And it says, oh, then I am currently pointing at the next thing I'm going to give you. It's holding on to that position because the next time you ask for the next thing in the list, it's going to give you that data. Let me show you what I mean. Well, let's talk about this for a second before we do this. It returned, this gets a little confusing, but it's not so bad. This function returns a key with list object, which means that it can't return null when it gets to the end of the list. It has to return a key with list object. Okay, it has to return that. You guys remember when we did sentinels? Right? The sentinel told you what about a set of numbers? That it was over. In this case, we are going to send back what I'm going to call a dummy key with list. And that dummy key with list is going to have the word percentage be -1. Can you ever have a -1 word percentage? Now, it's impossible. Right? There isn't any -1 word percentage. If you get a word percentage back, if you get a KWR object back, and the word percentage is -1, you've reached the end of the list. It's the sentinel, basically. Yeah.
And that next would be null.
Well, then the iterator would go to null. We're going to go over that at least twice. You'll see. Okay. Let me go through the example here so that we can show you what I'm talking about. Okay. You do have to populate a new dummy key with result object with the word percentage -1 to tell that you're at the end. It's like an iterator. Yeah.
So the first link in the list where next is null
Yeah.
has a dummy KWR.
No, it actually has a real one. I will show you. Wait, ask that question again at the end if you're so confused. I'm going to go over the actual thing in a minute. That's a very good question, but I want to show you what it actually means in principle. I'm going to go over it at least twice. Okay? Here's how you might do that, by the way. You might say, if you want to create a new key with word list, how do you create a new variable? Give the type, give a variable name. Type, variable name. I'm going to call it @end. And then I'm going to say at end.word percentage gets -1, and I'm going to return at end. That's how you return a dummy KWR. It's like you have to create it and then return it as a sentinel, basically. Okay? All right. Here's what we're going to go through this very slowly, one at a time, and you're going to ask all your questions now. At the beginning, you read in a list. Okay? When you read in a list, you've got the following. Okay? You've got, for phase 0, you're not going to have this stuff in there, but it doesn't really matter. Okay? When you call next, if you say mylist.next, here's what's going on. You've got the head pointing here. This is the first one. The iterator is pointing right here. How do we, or what do we return when we say next here? Any ideas? What actual KWR stuff gets returned when I say next right here? Ideas? What do you think? What do you think?
You kind of want to, so something on the head. So you go to the head and you find the next point, and so you go to the second one.
No, you don't need to do all that. Here's what's easier. The iterator is pointing to the thing that's going to return to you the next time you say next. So what's it pointing at right now? It's pointing at this object. It is going to return to you ABC123, 0.0, and this business. That's what it does. Where is the next point? Where is the iterator going to now point after this? It is going to move over here. So, again, we're going to go through this twice because I want you to get it in your brain. All right. There's what you return because the iterator already points there. The iterator is all set to return to you the next thing. It's already pointing at what it wants to return to you, and it's going to give that to you. But then it needs to move itself to the next one over. So where's the iterator going to point after this? It's going to point over here. Now, I asked this in the last class, and people gave me blank stares, and I was surprised. How do you make the iterator go from here to here? Talk to your neighbor about that, because a bunch of people still don't know how to do that. I want the actual C++ code I am going to make this go from here to here. Okay? Talk to your neighbor about that. Blinking over there. We are. Okay, good. Got this? Good.
Where is mylist.next? Where's that function?
It's going to be in your, probably in your phase 0. It's going to be your list.
Okay, but is there anything in the header file that I should look at?
No.
It wouldn't it just be point to the next?
What? What would?
The iterator?
No.
Okay.
You're getting there. Almost. Almost. Think about how you traverse a list in general. Okay, who wants to tell me what this is? Tony, go. Iterator gets iterator next. Okay? It's exactly like how we traverse any other list. What happens when you say that is the iterator starts here. Remember, it's trying, the number in this iterator is right now whatever the address here is. What we want to make it is the address here. Who currently holds this address? This guy does. This guy is part of what iterator is pointing at. So we can say iterator gets iterators next. The number here becomes the number in the iterator, meaning that the iterator moves to be pointing over here. Everybody get that one? That's the one that if you don't quite get that yet, you have to learn this. Otherwise, you'll never understand linked lists, and it's going to be bad news from there. So you've got to get that. But OK, let's do that. All right, there we go. We've said iterator gets iterator next. Now, let's keep going through this. I go and I say mylist.next. What gets returned? Jacob, what is it? Yeah, read off which one gets returned. Yeah, you return a KWR object that has password in it, 100 and some text. And then where does iterator go?
Iterator gets iterator next.
So it goes over there. Everybody with me there? One more time. Where does it? What gets returned now? Football 50. This business. So excitement, right? And then where does the iterator go? Iterator gets null. We are not quite done yet. What happens if I call mylist now, next now? What gets returned? Something has to get returned. We can't return null because we're not returning a pointer, we're returning an object. What gets returned right here? Catherine.
Is it the passage instance that you made with?
Yep, it'll be the instance that's made, the dummy one that has -1 for the word percentage. So let me write part of this function for you. If iterator equals null, right? Comment at end of list. Okay? So if we're at the end of the list, we'd better create. By the way, you can't just say. You can't just say return. You can't just say return iterator arrow this and then iterator gets iterator next. Any idea why you can't do that? Yeah.
Because return breaks out of the function.
Once you return, you're out of the function. So you can't return something and then try something else. Do anything else. You can't do that. But in this case, so we're at the end of the list. So now, as Catherine said, oh, if we're at the end of the list, we'd better return a sentinel. We better create that sentinel. Key with result at end. At end dot word percentage, I'm abbreviating, gets -1. Right? Iterator, oh no, that's not even going to change. Iterator is not going to change at all. We are going to now return, what do we call it? At end. Done. Zach. That's WP is just word percentage. I abbreviated. Yeah.
Besides like this end part, what's the difference between the iterator and just like the current?
Sure. The iterator is acting as the current one, but we only want it to change when we ask for the next one. Okay. So the iterator is going. So we're going to do a bunch of stuff, and then we're going to say, oh, give me the next one, and do a bunch of stuff, and then give me the next one, and give me the next one. And internally to your list, it's going to say, okay, I'm queued up to give you the next one. Okay. All right. Let's go through this one more time because this is a little mind bending for people who haven't seen this before. Most of you guys. All right. What gets returned here? This one. Where does the iterator go? Here. What gets returned here? This one. Where does the iterator go? Here. What gets returned here? This one. Where does the iterator go? It becomes null. What gets returned when we say mylist next? A dummy key with result with a word percentage of -1. That's this stuff down here. And the iterator does not change. What if I ask for next again? What gets returned? Say another dummy. It just will give you a dummy all day until you reset the iterator. It just keeps going. Look, you're still at the end of the list, you knucklehead. All right, keeps going and keeps doing that. Okay? Questions on this? Yes?
Can you explain again how how like next like actually moves the iterator from one to the other. Right? Yeah. All right.
Right? It says iterator gets iterator next because it starts pointing at this one, and then you say iterator gets iterator next, and that moves to this one, and iterator gets iterator next, moves to this one. Iterator gets iterator next, moves to null. And then you'd better check if it's null because you can't say null gets null next or you get a seg fault.
What type is iterator?
It is a node pointer,
Okay.
just like the head. Good. Anna.
Where do you reset it?
Ah, where do you reset it in your code or what happens when you reset it?
Yeah, well,
Okay, if you say mylist.reset iterator, it just moves the iterator to point back at the head. It's a one-liner function. Well, yeah, good.
Will iterator be defined in our private?
Yes, iterator is a private variable.
Cool. And then
Yep.
the same with head probably.
Head is a private variable as well. The only two private variables you have in the list.
Or it could be a constant.
What can be a constant?
Head.
Can't be a constant because
Maybe we'll
it starts at null and then you have to use new every time you insert. Remember, just go back to your insert to see what it is. Yes?
So next is returning a KWR,
Next is returning a KWR.
but if we have to reset, or we have to switch the iterator to the next one before we return. So does that mean we have to use a temp?
Yeah, you would have to use a temp to do that because you can't, you're absolutely right, you can't return it. You just use a temp, do exactly this, say key with result, to return, or key with result KWR gets iterator arrow KWR. That's the temporary one. Or you can call it temp, whatever, return temp at the end. Now, you'd have to figure out the logic for that. But do you get the iterator now? The iterator is just saying, hey, I want to walk through this class one at a time. You will use this a billion times in various programming languages. If you ever go program in Python, use it all the time. If you ever go program in some other languages, you use these iterators very frequently. It just means, hey, I'm walking through the list one at a time. Give me the next one. That's all it means. Okay? All right. That was phase 0. Phase 1, what are we doing? We are building this dictionary class. The dictionary class has a constructor. Dictionary class has a destructor. The dictionary class has a has-word function. The dictionary class does not even have an insert function because we have created a read file function for you, which just populates your list all for you. Populates it for you. Okay? So you don't need to worry about that. You know what? I think I wrote it wrong. This just popped into my head. I think I wrote it a little bit wrong. I'm going to go check. Yep, I'm going to go check. I think it needs one other part to it. Because this is the next function. The expand function you need to write. Yeah, I believe. Well, I'll have to check. Let me check right now. Now that I'm thinking about it, because let me see. If I do, I will have to change it right after class. Vim comp11 files, proj to dictionary.h. No, .cpp. Okay, let's see. Reads it in. Oh no, I do. Whew, I did do it right. Whew. Here, let's look at what this read file does. The read file, or read dictionary from file, read dict from file, takes this file name. The file name is going to be in your header file. It's going to be built into your header file. And what it does, all this IF stream business, we'll get to that maybe at the end of class, if not the beginning of Thursday. It opens the file up and it starts reading in word for word, and then it just populates your dynamic array. It says the next one is going to be the next word, and you increment the number of elements. If the number of elements is the capacity, you'd better expand. Okay, I forgot that I wrote that part. Oh well. Anyway, I did. So and then you just keep doing it and it reads it all in. So there's no need for an insert function here because you're going to do it all at once, and you do it all at once, and that's it. Okay. All right. Let's see. That was that. And let's go back to there. OK. Expand function. All right. And then you're going to have to create the phase1.cpp file. You would be very smart if you simply copied your phase0.cpp file to phase1.cpp and modified that. because phase 1 is going to be very similar in form. It's still going to have to do the regular encryption, it's still going to have to do the regular decryption. The brute force function is going to be different. Okay, so basically you're going to modify phase 0.cbp to update the brute force function, and then you're going to have to add some other functions. Remember, for your dictionary, you're going to have to add functions that actually do something to tell whether or not how many words are in the sentence that are in the dictionary. For instance, a check sentence function, which sees how many words from the sentence are in the dictionary. Okay, those are the things you're going to have to do for phase 1. And you're also going to have to determine the top 5 matches. That will take a little bit of logic, but is not impossible. So this week's lab is going to be all about strings. Okay? And did I mention that I forgot to tell you about the pre-lab? Technically, there is a pre-lab for this lab this week. If you don't have time, like I know some people are going to lab right after this. You haven't even seen the pre-lab yet. Just read it over before you get there. If you don't have time to do it, I'm sorry, but you'll review it in class. For those of you who have a little more time, hopefully you'll get to it. But I apologize. I totally forgot to tell you there's a pre-lab. But don't worry if you didn't do it. Obviously, you didn't do it. You didn't have time. OK, but anyway, we're going to talk. This lab is going to talk about strings. Turns out strings are just objects. Dirty little secret. I never told you this at the beginning of the year. Strings are just objects, which means they have functions like length. If you have a string s that has a, b, c, d, e in it, you can do s.length, parenthesis, parenthesis, which is a function within the string object. And if you do s.length, in this case, it will give you 5. So s.length equals 5 is true. Yeah?
Is length a built-in function?
It's a built-in function. Yeah, it's nice. It's a built-in function for you, which is cool. There's a few built-in functions. That's the one you're going to care the most about, right? What's cool about strings is under the covers, they're just character arrays, regular old character arrays. But they have functions in them. The character arrays are dynamic arrays, and they have their own expand function. They have everything they need to do that. It's very nice. Okay? Just strings of characters. C++ actually is really nice. It overloads the bracket notation so that you can say s bracket 3, and that means, in this case, 0, 1, 2, 3. S bracket 3 is D. If you say char ch gets s bracket 1, well, s bracket 1 is the char b, so then ch gets set to b. Very nice. That means that you can read through these strings. So if you have, let's erase this. We're now no longer in linked list territory. We're actually into string territory. There we go again. This happens every time, doesn't it? So bizarre. Maybe it's on a timer of some sort. Anyway. OK, so what we're going to have is things like this. If we have the quick brown fox, OK, the quick brown fox, if it's in string form, right, is simply going to be the character array, the quick brown fox. Here's character 0, 1, 2. The space is character 3. 4, 5, 6, 7, 8. Here's another space, 9. 10, 11, 12, 13, 14. 15, 16, 17, 18. If this was a string sentence, let's say, string sentence, we'll just call it sent for sentence. If it was a string sentence, right, and I said sentence dot length, what would I get back? Don't say 18. 19, right? Because it starts at 0, right? OK, so that's what we can do there. Sentence dot length is 19. If I say sentence bracket 3, what do I get? A space, right? If I wanted to figure out what the words in here are, what am I going to be looking for? Spaces, right? If I know how long this is, can't I just walk through this array looking for spaces and walk through this entire string one character at a time using a for loop and keep track of where the letters are until I get to a space, at which point I know I have a word, and then I send the word to the dictionary. Does that make sense?
How would you take those letters into a word?
Good question. Okay, uh-oh, looks like this is actually broken. Let's see if we can do this. Doesn't really matter. We can go through the rest of this without it. But, oh, I just saw a light come on up there. Come on, hang on. Let's see, we're going to do this. And then, sorry, I just need to turn off the, oh, it's back. Okay. Very slowly back. Okay. So we've got our strings here. The question is, how do you keep track of those? Well, you're going to have to do some of that logic. I'm not going to tell you exactly how to do that, but I will tell you that you can loop through and you can add to a new string very easily. In fact, this is going to come up in a couple slides, but I might as well do it now because the question was asked. If I say string, let's say word. OK, what does that start out as? It's actually not a dead squirrel, although I've been kind of saying that the whole year. It's not a dead squirrel. It starts out as the empty string because it's got a constructor in there, and it's smart. It's an object, and they say, well, look, what do I want to make the string when it starts out? The empty string. So if I say string word, it's already the empty string. You can actually append to the word like this. You can say word plus gets A. Now what is the word? A. If I then say word plus gets B, what's the word now? AB. Do you see how that works? You can just append to a word one at a time. So logically, I'm not going to tell you how to do this because I want you to think about it and figure it out. If I'm going through here, I'm going to go, look, is that a character? Yup, append it to my word. Is that a character? Yup, append it to my word. Is that a character? Yup, append it to my word. Is that a character? No, it's a space. Stop appending to my word. Go check the word in the dictionary. Update the number of words and update the number and update whether or not it's a word in the dictionary. You see how that logic works? You just have to go through the whole thing using a for loop. You know how long the string is. Yeah.
Where is all these, where are the files for string? Is it in namespace?
Where are the files for string? So I don't think you can see those directly very easily. They're built into the library, which you don't have direct access to. You can get it. It's all open source, but it's not easily findable. Yes?
What else are you not telling us?
What else am I not telling you? Yeah, there's a few things I'm not telling you. By the way, if you want to look up the string functions, right? I mean, I'm not saying this because I don't want you to ever look these things up. If you want to look up the string functions, just go to Google and type up C++ string reference, right? And you will go to the string reference here. It's like the first link, right? And if I click on the first link, there we go. And if the first link, it comes up and it says, oh, here's the class. Let me make this a little bigger for you. OK, it says strings are objects. Oh, look, I didn't lie to you. That represent sequences of characters. OK, standard string class, blah, 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 blah. Hey, look, here's all the members. You've got, oh, those are all the actual, oh, look, a string has an iterator in it. Ooh, these days it does. It used to not. That means the newer one. But you don't need to use the iterator. You could if you wanted to. It's got all these other things. OK, look at all the functions. It's got a constructor. It's got a destructor. It's got an you don't need to worry about this till you get to comp 15. It's got some iterators in it. It's got a capacity. Oh, look, it's got a size. It's got a length. It's got a max size. It's got a resize. It's got a capacity. It's got a reserve. It's got all these functions. It's got a shrink to fit, which is a new function. It's got the bracket, which means you can get a character using the bracket notation. It's got plus gets, which means you can append to it, like we did right here. All these functions. It's got a swap function to swap two string values. Blah, blah, blah. Lots of functions there. So that's all what I'm not telling you. All right? Lots of stuff you can go look up if you want. Gavin.
So you have to use
You do not. IOStream already has the string built in. Yeah, you probably should, when you do IOStream, also do pound include string, but IOStream generally includes it. Yeah, good question. All right. So I'm going to dig down a little bit. We're going to go a little low level here for a few minutes, OK? Bear with me on this. Much of this you don't really need to know, but start thinking about it. When you get to Comp 40, you'll use it. Right here, we say int string slen gets string length, and then I use slen in here. Why do we first get the string length instead of just in here saying I is less than s dot length? There are two reasons, one of which you might be able to figure out. The other one you probably won't because it's brand new. Any idea why I might not want to call the string length function every time going through loop? Yeah?
Is it somehow like it takes longer or it's more flawed or something if you are running through the string while also checking its length the whole same time?
Almost. It is inefficient to call a function. It's much more efficient to check a variable. Checking a variable doesn't mean going and calling a function and doing all the stuff. It just means what's the variable. Now, is it really that much of a difference? No. But it's enough that we generally like to say, OK, fine. If you're going to walk through an entire list, just store the value of the length first. And just use that because it's cheaper in time to check the length instead of to go through and actually call the length function. It's very good. OK, that's the one reason. Now, the other reason is that if you wrote the following, if you wrote instead of s underscore len here, you wrote s dot length, you would get a warning. And the warning would be something like loss of precision due to converting implicitly two variables, blah, blah, blah. And you'll go, what does that mean? And I'm already expecting everybody who's not in lecture today to put this on Piazza when they get this warning. And I'm going to go, go see the lecture. But the thing is, you will get a warning if you did that. Here's why. Now, this is the lower level stuff. OK, this is the efficient part. It turns out that the length does not return an int to you. So if we say int I gets 0, I is less than s dot length, it's not actually an int. However, it is an integer. All right. Now, here's I know this. You're gonna think I'm crazy. You're gonna think computer engineers are crazy. But hold on a second. All right. We have the int type. OK. Int x gives me a variable x that can hold up to a certain number of integers. Like it goes all the way up to some number, and it's got a high number. You can't go any higher than that. On your computer that's sitting in front of you, the odds are very good that your int will be 32 bits long. We've talked a little bit about what this means, but really what it is your integer is a bunch of ones and zeros. It's a bunch of ones and zeros, and it can hold up to 32 of those to determine what your number is. You know how the first slide on every slideshow is that day of the month, and that day of the month is like 100010, whatever, right? That is binary. It's like 5-digit binary number. Ints can generally hold 32, but we don't know exactly for every, depending on which, it depends on which computer you're using. This is a shame. It turns out that the people who created C decided to make ints dependent on the type of computer you're using. Why would they do that? Well, they decided to do that because there were lots of different types of computers then, and they said, well, we want the int variable to be able to grow with various computers. If you have a 1970s computer, it might have an 8-bit integer or a 16-bit integer. In fact, your computers have the ability to have 64-bit integers, but generally they still leave int at 32 for some reason. Does anyone know what 2 to the 32 roughly is in real numbers? Jacob?
42949.
Did you just do that? You did. It's about 4 billion. Okay? So ints can hold up to 4 billion different numbers, but it turns out half of them are negative. So it can actually only go up to about 2 billion, and it can go down to about negative 2 billion. Okay? Ints can do that. Well, it turns out that when the people who wrote the string class and the people who wrote C++, they said, we don't like this ability, this unknown quantity. We don't like it that you don't know how big your integer is, unless you can check. And I'm going to show you in a sec how you check how big it is. But we don't like that. C++ said that. So they said, let's create another type of variable, another type of integer where we're going to define how long it is. They called that a size underscore t. A size underscore t is an integer. It just happens to not be an int. It happens to be a, I believe it's a 32, or actually I believe it's a 64-bit integer. On any C++ computer you go to, you can do size underscore t and it'll be a 64-bit integer. Okay? And that's how long it's going to be. It's, yeah.
So why do we write using ints and not size t?
Good question. Because int's a little easier to remember, and it doesn't matter most of the time. And here's the other thing about size t's. Size t's, you know what, now that I think about it, size t's might also have they may also have a different amount, but I believe they're all fixed. I'll have to look into that. But the idea is that they made this up to make it a little easier to do things. The other thing about size t is, okay, everybody do this right now in their head. Take your first name, figure out if your first name was a string and you said s.length on it, give me the number back. 4, 7, 5, 8. People with long names like, right? My name's Christopher, right? And anybody other Christophers in here? So with the name Christopher, it used to be this way. The SATs would only have 10 letters for your first name. And it's got 11, Christopher has 11 letters. So every Christopher would get the SATs back and would say Christopher. Well, that's my name on the SAT as far as the SAT is concerned. Anyway, did anyone give me a negative number? No, of course not, because length is not negative. Size underscore t's are also what we call unsigned, which means they don't have this negative business. They only are positive numbers. OK, what does that really mean? Well, first of all, it means this. It means that when you say size underscore t size, right, or size underscore t, you know that it's going to be unsigned. If we want to find out how long they are, there's a little function you can use that you'll use in Comp 40 all the time called size of, and you give it a type, and it tells you how big that type is, built into C++. All right, if we run this, in fact, we can run this over here. Let's see. It is called size of ints. Size of ints. The integer size for ints, int, is 4 8-bit numbers. What's 4 times 8? 32. So it's a 32-bit number. Size underscore t size is 8 times 8, which is a 64-bit number. OK. So why do we care about that? Well, we care about that because this is what it returns, and you get warnings if you don't do it the way. If you don't do it this way, you get a warning there. Sean.
So C++ doesn't care that we're assigning a size.
Yeah, you mean here?
Yeah.
I don't know why it doesn't do that.
Probably not.
I've got one. I don't know why it doesn't give you a warning. It should, but it doesn't. So you can do it this way. I don't know. I'll give you one other thing in a second about that. Sean, any other question? Sean?
Yeah, I was trying to do an Euler problem that had a much longer than int.
Oh, OK.
And it tried to tell me that I couldn't do it in conversion from int to long another variable type.
Long is another variable type, although ints and longs are in most cases the same, as it turns out, or 64 and 32. 64 for longs. Yeah. So we'll get to I'll get to yours in a second. Your comment in a second. Because things are unsigned, size underscore t's, because they're unsigned, cannot hold negative values. What do you think is going to happen if I try to set size or x here to -1? What are my options? What could happen? Error. It could be an error, could be a warning. What else? Seg fault. What else?
Either print positive one or loop back.
Either print positive one or loop back. It's not going to print positive one, but it will print the following. 1-844-674-440-737-09551-615, which happens to be 2 raised to the 64 minus 1. Because it wraps around to the end, and that's the biggest number that can be held. -1 says, oh, I can't hold -1, so I'm going to hold the biggest number, and it just wraps around. It has to do with the binary representation. Again, you'll get to that in Comp 40 if you get up to that point. Okay? So let's go back to Will's question for a second. Why don't we get warnings? I'm not sure why we don't get warnings for this. If you do a -W conversion warning, you want instead of just -wall and Wextra, it will give you a warning for both of these. It'll say here, it'll say you're trying to convert an int to a size type. Actually, that's the other one. Let's see. It is here. slen gets slength. You are trying to convert a size type to an int. It gives you that warning.
It seems to get super mad because it just says implicit conversion. What is that? Loses integer precision.
This one loses integer precision.
Just like letting you know, like, oh, you might lose some.
Right. If you have instead of 32 bits, you have a 50-bit number. Well, you're going to lose that because it only holds 32 bits. Yeah, truncates it or whatever. Right. And then this one says, oh, you're trying to use a size type to an int. Maybe this is why it gives you the warning before, because this is all you're trying to do is you're trying to. It doesn't care about this one as much as it cares about the signedness. Anyway, point is that if you use dash conversion to this. Now, remember how we're using all these warning flags, W all and W extra? W all, -W all, should give you all the warnings, but it doesn't. There's a historical reason why that's the case, but not that important. W extra should give you all the extra warnings that W all doesn't give you, but it still doesn't give you all of them. It doesn't give you, for instance, -W conversion. There is one called, by the way, if you do this, size t slang gets slang, and then you do size t, it will give you no error, no warnings, because that's the proper type, right? Length returns a size t, and in here you're going through a size t, and it would work fine. Turns out there is a -W everything, which is supposed to be all the warnings. Every warning Clang knows about, it goes, fine, that's W everything. Some of them you don't want, actually. I ran this on some of the code I gave you, and it gave me like 20 warnings. And some of them are like really arcane warnings that you will never have to worry about. And in fact, I looked it up on Stack Overflow, and they said, yeah, if you get that particular warning, it means you've turned on too many warnings. Because you never care about that. And so it's too bad. This is why we don't make you do W everything, because you'll get these weird warnings that'll mean nothing to you and not be important at all. So stick with -wall and -wextra, and if you want to add -W conversion, you can. It'll give you some more warnings. Okay? All right. We talked about appending a string just by using the plus gets on there. You can look at the code up here. And the parsing of text. This is the part where you have to walk through the quick brown fox business and pick out the word. I'm going to let you guys figure out that logic because it's kind of fun to figure out and it's a little tricky. This week's lab will be really important. So I'm not going to go into reading files today. It doesn't matter yet anyway. I'll do that starting on Thursday. Questions? I will see you in lab.